back in chapter 4, we had discussed a concept called inertia. And I'm sure you remember what inertia is. Inertia is the tendency of matter to persist in its state of rest or uniform motion in a straight line, right? And inertia is the reason why Newton's first law is true. So just to remind you what inertia was from chapter 4, suppose you have an object that's at rest, right? It would just want to be at rest. If you want to apply any if you want that object to start moving, you would have to apply a force. So if the object is at rest, it would just want to be at rest. And if the object is moving with some velocity, then you would have to apply a force in order to change that. So if you have an object out in space and there is no force being applied to it at all, you just throw the object once, so it's moving with a constant velocity, then it will just continue moving with that same speed in the same direction forever, if there is no force acting on it. So that is Newton's first law. And the reason Newton's first law is true is because of the property of inertia, right? So inertia is a measure of how hard it is to change the state of motion of an object, which really means how hard is it to change the velocity of an object. Right, so that was inertia. Now there is something very similar in the rotational world, and that's called rotational inertia. So the rotational inertia, which is also called moment of inertia. So remember that these two terms are synonymous. Moment of inertia and rotational inertia mean exactly the same thing. The old textbooks say moment of inertia, and newer textbooks, I think, are trying to switch that to rotational inertia, but they really mean the same thing. I'm used to saying moment of inertia. So the moment of inertia of an object is a quantity that determines how hard it is to change the object's rotational state, or more precisely, its angular velocity, omega. So if an object has a certain omega, it's rotating with a certain omega, the rotational inertia is a measure of how hard it is to change that omega, right? And there's nothing new in this, like you're all familiar with this concept in your daily lives. If you take a look at these two objects over here, on the left, what you have here is called a flywheel. It's an industrial flywheel, and it has many, many uses. Basically, what it does is that it's this large, it's this very thick cylindrical object, very, very heavy, and it rotates about its axis, right? And it's constructed in such a way that it rotates practically with zero friction. So you have these very nice ball bearing arrangement, so that there is hardly any friction at all when it's spinning. And I believe when they're actually used, they're put inside a evacuated chamber, so that you also have very little air resistance. So this is designed to just spin and with very little friction or air resistance. Now you can imagine that if this thing were spinning really fast, right, you would not want to try to stop it by putting your hand on it, right? It would probably tear off some skin if you try to stop it by putting your hand on it. So this has a very large moment of inertia, and so it's very hard to get this to stop spinning when it's already spinning. Also, it would be very hard to get it to start spinning when it's at rest. So that's also probably not something that a human being can do by just giving it a few pushes. It would be very hard to get it to start spinning at a high speed. So this has a very high moment of inertia. Whereas just imagine this little disk over here in its disk drive. So if this is spinning, even if it's spinning very rapidly, you can very easily get it to stop. Just put your finger on it and it'll stop. And also, if you want to spin it up, you can do that with your finger too. Just give it a few pushes and it'll start spinning pretty fast, right? So this has a low moment of inertia. That makes sense? So moment of inertia is a concept, is a quantity which determines how hard it is to change the omega of an object. And it's completely analogous to inertia that we learned in chapter 4. All right, now how do we measure moment of inertia? We're going to start with the moment of inertia of the simplest possible thing. Suppose I have this, suppose this is a horizontal plane. The plane of the board is a horizontal plane. And I have a point O over here, right? It's a pivot point. I have this rod this very, very thin, almost massless but rigid rod. So we can ignore the mass of the yellow rod. At the end of the rod, I've got this point mass, which has mass m, and the length of the rod is r. So the mass of the rod can be completely ignored. At the end of the rod, I've got this point mass m, right? The point mass also, the dimensions of that can be completely ignored. So that's why it's called a point mass. Now, let's say that I set, and the point mass m is also sitting on a frictionless surface. So everything is frictionless. So let's say that I set this rotating. So I just give this point mass a little whack and it'll start rotating. So what is the moment of inertia of a point mass as it rotates about an axis through O perpendicular to the page? So basically, the axis is very, very important. Whenever you're talking about a moment of inertia, you have to specify what axis the object is rotating about. In our case, the axis is an imaginary line which is perpendicular to the plane passing through O, and m is rotating around that axis with radius r, right? So what is its moment of inertia? I'll just write down the answer for you. The moment of inertia, the symbol for that is I. The moment of inertia of a point mass, which is rotating about radius r, rotating about an axis with radius r, is given by m times r square. You can think of that as the definition of moment of inertia of a point mass. That makes sense? All right. Okay. Everybody clear about that? That's how you get the moment of inertia of a point mass. Now, what about 2-point masses? Suppose I've got the, this rod is longer and it goes all the way to the other end as well. And at the other end of the rod, I've got another point mass, right? And let's say that these 2-point masses have different masses. So this one has mass m1 and this one has mass m2. Actually, why not make it a little more complicated? So why not make this other side of the rod longer? So suppose this one is longer and the point mass m2 is located over here. All right. And this whole thing is pivoting around the point O. So essentially what's happening is that m1 is describing this smaller circle. So if just imagine this whole yellow rod is pivoting around the point O. So M1 will describe this smaller circle. And what about M2? M2 will trace out this larger circle, right? And the radius of the circle described by M1 is R1. And the radius of the circle described by M2 is R2, right? And in both cases, the yellow rods have zero mass. So you can ignore any effect due to the yellow rods. The only purpose for them is to ensure that these M1 and M2 go around in a circle around O. So now what is the moment of inertia of the 2-point masses? Both of them are rotating about the same axis, which is the imaginary line passing through O. What is the moment of inertia of these 2-point masses going to be? See if you can figure it out yourself and write down the answer in your notebook. The important point here is that moments of inertia about the same axis are additive, so you can add them up. So as long as you're calculating the moment of inertia about the same axis, you can feel free to add them up. So the total moment of inertia of these 2-point masses, only because they're rotating about the same axis, would be m1 r1 square. That's the moment of inertia of the first one, plus m2 r2 square. Only because they're rotating about the same axis. So I'll write this down. Moment of inertias about the same axis are additive. So you can just feel free to add them up. That makes sense? All right. So we know how to calculate the moment of inertia of a single point mass that's rotating about a certain axis with radius r. And if there are more point masses rotating about that axis, we know how to find the overall moment of inertia, right? The same thing would apply if I add a branch to this rod and stick this branch over here and put another point mass at the end of this branch, M3. This the way I drew it, this would have the same radius as the first one, R1. So if you wanted to find the moment of inertia of this tree with 3 branches, which is rotating about the point O, you would just do another m3 r3 square, something like that. That makes sense? So moments of inertia about the same axis can be added. Now, how would you find the moment of inertia of an extended object? That's what we're really interested in. Instead of a point mass, suppose I have something like this weird shape. And let's say, actually, let me just not, rather than a weird shape, let's just take this disk. Suppose I want to find the moment of inertia of this solid disk. And it's rotating about an axis which passes through the center of the disk and is perpendicular to the disk. So that's my axis. Notice that I always specify the axis whenever I talk about moment of inertia. And I want to find the moment of inertia of this whole disk. So how would I do that? Here is how I can do it conceptually. So what I can do is I can break this disk up into small segments. So here is one of my segments. Let's say that this segment has a mass m1 and it's at a radius r1 from the axis of rotation, right? Then I can make another segment somewhere over here, call this as m2, and this is at a radius r2 from the axis of rotation. So I have broken up this whole disk into many little segments like this. Here is m3, which is at a distance r3, right? So if I can do that, then conceptually I can write down the moment of inertia of the whole disk as I is equal to m1 r1 square plus m2 r2 square plus m3 r3 square, and so on, simply because when the disk rotates, all these segments will all rotate together, right? And moments of inertia about the same axis are additive. So that means I can feel free to add up the moments of inertia of all these segments and get the overall moment of inertia of the disk. That makes sense? Everybody clear about that? So in other words, I can write the moment of inertia of the disk as summation mi ri square, where i's are all of the individual segments that I broke the disk up into. Now, this answer would not be super accurate because I'm taking a finite segment, this M1, M2. These are small, but they're still finite segments, right? And every point in M1 does not have the same radius R1, and that's an approximation that I'm making. So how can I make this formula more exact? What I can do is I have to make my individual segments, the M1s, M2s, I want to make them as tiny as I possibly can, right? The tinier I can make these segments, the more accurate this result will be. So to get the most accurate answer, what I need to do is I is equal to the limit of each of these m's tending to 0, and then take the sum, mi ri square. So if I take this limit, that means I'm making each of these little segments that I broke the whole thing up into as tiny as I possibly can, right? I'm taking the limit that they are so small that they're practically 0. So limit mi tends to 0, summation mi ri square. If I do this, then this limit actually becomes an integral, and the integral will look like this. And I'm skipping over the mathematical details. They're not super important, but the integral will look like this r square dm. So this integral is the accurate answer for the moment of inertia of a extended object. Extended object means something that has actual dimensions is not a point mass. So we've learned how to calculate the moment of inertia of a point mass, it's mr square. And by extending that idea, we can find the moment of inertia that's something that's not a point mass, right? We just break it up into small segments, which we treat as point masses. And if you make those segments truly tiny, then that sum just turns into an integral, right? And that integral is r square dm. All right, so that's what I have on the slide here. The moment of inertia of a point mass is mr square. And for an extended object, you break up the object into small segments, add up the moment of inertias of all of these small segments. And to make the answer exact, you have to take the limit where each segment that you're breaking it up into is vanishingly small. It truly becomes a point mass. Then the answer will be exact, and then it turns into this integral.